Good afternoon, everyone. Thank you for making it along to the last session of the day. I'll be sure to be extremely long and run well past 5 o'clock. No, I definitely won't do that. So TCS, as you're hearing, spun out from Glasgow University back in 2014, actually, but we properly started going in 2015. And 2018, we moved into our own premises just to the west of Glasgow, which has really been a big boost to the business, getting out from the university's wings. So we provide a wide range of thermoelectric-based systems, whether it's generating power from the devices, going into cooling systems, which I'll go into a lot more detail on here, and associated technologies that go into numerous different markets. Thermal management is a universal problem, and it's only getting worse as everything heats up. So to give you a little bit more information, I'll talk first about thermoelectric cooling, an overview of various products and capabilities in that area. And then I'll go into a bit about our test equipment for understanding how the devices work, and then a little bit into options on consultancy and generating power from these devices. So this will be quite a wide-ranging talk, but it will be very thermoelectric focused. So before I get into detail of all the different varieties of cooler we have, the fundamental technology is based on a semiconductor device, so a lot of N and P type junctions connected together electrically in series and thermally in parallel, so they become almost like two parts of a sandwich. When you apply a DC current to that sandwich, you get electron transfer through DC, but you also get photon transfer, which is heat. And that photon transfer causes the heat differential or the temperature difference that generates the cooling effect that you see. Devices also operate in reverse, so you can reverse the DC current, and you can generate heat or cause the temperature difference in the opposite direction. They also operate to generate power. I'll go into a lot more information on that later on. So I think probably the most important part of this slide is to get over to you how wide the operating temperature range of these devices is. Right the way down from below -40 up to +80. From a single device, there's no other parts to it, there's no additional heat sinks or heat exchangers or electronics. You can choose your operating range and you can achieve the temperature you want. These devices are inherently reliable. N-P type semiconductors are ubiquitous nowadays, and we rely on them without even knowing about it. To give you an example application, this is targeted for a grocery locker where the customers were wanting to be able to chill fresh goods and in the same locker compartment at a different time with a different customer, go down to freezer temperatures. So have the ability to go down to 3 or 4 star freezer temperatures. So this takes, if you were to compare this to a sort of standard vapor compression, you normally have to leave your fridge freezer 24 hours or at least sort of 48 hours before it gets down to that temperature. We do this in minutes. We're talking about maximum we can do it in is about 30 minutes, but the graph shown here goes down to takes about 75 minutes to get down to the right temperature. And even quicker than that, it can go up to 80 degrees C. So you've got here a much more versatile and flexible device in a much smaller package. And I'll tell you a little bit more about the comparisons versus vapor compression later on. It's not all based on the devices. You also have to understand the control methodology and the electronics behind it. Essentially, it's still a piece of electronics that you're controlling, so you need to understand what the limitations are, and that goes right down to the device level. So you need to care about your cooling capacity and how much power you're putting into the device to get the most power out of it. They actually can operate almost as heaters without you realizing it. You can stray into the operating area of the curve where the device actually becomes a heater rather than a cooler. So you need to take a bit of care as to understanding how these things work. There's various ways to operate these devices, not just from a set point, but you can operate it as a standard thermostat control, which you'll all be familiar with in our houses, with auto defrost if you need it. But you don't just extend it into domestic environments. It becomes an industrial unit when you can begin to automate temperature cycling and even humidity as well. Not quite at the stage where we've got an app, but it's not far off. But other than that, everything is possible in the world of interfaces these days. You get a lot of flexibility about how these systems work with bigger units. So you tend to not just have one locker deployed, you would maybe have a bank of 50 deployed. And you need complete control over every single one of them to make sure that you're meeting your customer requirements. So what we have from this particular customer was a bank of 20 lockers, each one kitted out with our cooling technology, and the customer has the complete control of which compartment is on, not only on, but also which compartment's cooling or heating. So in the past where you had the entire system limited to only being coolers, you now have the ability to turn certain parts of the system off, save your electricity bill, and turn certain parts of it on when they're needed, and only when they're needed. This extends much more into the internet using various protocols. MQTT is a fairly standard message interface, and layers of protection keep the whole system secure. Becomes more of an industrial unit that's suitable or hardened, that's deployable to the rest of the world. Again, you get something as simple as a touchscreen or some LEDs on the front panel to a lot more sophisticated Windows app or a system for your phone. Multiple channels can be connected together. We are led by by your requirements, by the customer's requirements, and if there are parts of it that aren't needed or that need to be upgraded, then that's possible. Just the sort of the one thing that's probably the more important of this is your reliability. 100,000 hours, you're probably going to need to clean your heat sinks, but comparison with the compressor or vapor compression system, it's a marked improvement. 100,000 hours is probably lowballing it a little bit. These devices, or the same technology, was used in the Voyager spacecraft that departed our solar system a while ago. I think it was launched before I was born, and it's still generating power to send back data back to NASA. One point though is on power consumption. They generally do consume a bit more power than typical refrigeration cycles, but what you lose on power, you gain in flexibility and the ability to sort of save energy by turning it off when it's not needed. And again, complete software control, which is very limited when it comes to switching on compressors that they do the same job every day. There's various incarnations. We've all seen, you may or may not have seen, standard little laser coolers that are generally where these devices have found their application in the past. They scale massively. We're talking about kilowatts of heat that can be pumped, can be rejected, can be transferred. This application is a very simple air source heat pump. And don't think of air source heat pump as needing huge air conditioning units sit outside the back of your house. You're talking about air conditioning units that can sit in the space of your boiler. This one, for example, you could attach to a spa if you're so inclined. Another example, if during lockdown you also bought a little jacuzzi or a little blow-up pool spa, then you can tie the heat pump to your conservatory, taking the excess heat out your conservatory, dumping it into your nicely heated spa, and enjoying the benefits of that 40-degree heat. The applications here, they're meant to be general, to give you an idea of what's possible. There really is a world of opportunity that these devices can unlock. One thing that is tricky with electronic devices is accelerated life testing, and this is a system we're built for various manufacturers of battery technologies, and being able to accelerate and cycle their systems is another sort of industrial benefit of these systems. We're looking at the ability to replace your gas heater with your gas boiler with a thermoelectric based solution. They've got all the benefits of the thermoelectric devices, so you can install it onto your wall. You don't need that gas engineer to come out and you can reject the heat up your central heating, and also heat up your hot water for your sink, because there's nothing worse than turn the tap on and waiting about half a minute before your gas heater kicks in and actually delivers that hot water that you want. So we're sort of still looking for someone with a sheet metal working background to form the boiler shell. So that takes me really quickly through the coolers. I'm going to talk a bit about testing devices. This was a very heavily academic pastime. I call it pastime. Very heavy academic sort of focus. Understanding how lots of different materials work was the key to unlocking the efficiencies that we now have in the past. So we've worked with universities all over the world in developing test systems that enable them to really understand their devices and explore the efficiencies that are possible. So there's various systems we've built for different manufacturers over the years, from thin film devices that are millimeters in size, that are very fragile, up to and the data that sort of goes alongside it, and the data capture, which is every researcher's dream, to larger numbers of device testing for multiple larger scale replacements of different devices. So there's numerous aspects that we can approach any work, and we often design custom test equipment. This looks massively Heath Robinson, and honestly it was, but it worked, and it got the devices tested to the right specification. This is a multiple channel system that was actually deployed onto a ferry, capturing waste heat. I didn't explain exactly how the power generation side of it works, and this is probably a good opportunity to do it now. So that same sandwich I described earlier, if you place that sandwich between a hot face and a cold face, getting that temperature difference, you can generate DC power. We're not talking huge efficiencies. Device efficiency is usually about 5 to 6%. But if it's waste is waste. Let's take whatever we can get. This is a system that was deployed onto a ship to capture data from the marine engine, which is, they're in the megawatt territories, to extract some power and turn it into something more useful. Multiple custom parts were made as part of the project, and a huge number of chillers and fixtures were made up to capture that all-important data that proved that their system captured and stored the energy and could extract the energy from it. We moved on to doing far more exotic systems, and a lot of this work has actually fed into our current generation of products. So working with universities to really understand their devices means that we can take the technology they've developed and license it and take it into our products, which is why you won't find the efficiencies that we have on the market elsewhere. I'll talk a little bit about power generation. A lot of the discussions we'd had in the past as a company were, well, why do you even bother? Power generation is, you're taking it from a waste, so can I not just put my battery straight across the thermoelectric? And there are plenty of people trying to do this, and they found that it didn't work. Essentially, the device operates similar to a solar panel, so it's got the same sort of long power curve and then steep drop, and that's sort of the power versus voltage curve. Thermoelectrics are a little bit more linear, and that does not translate from, you cannot put maximum power point tracking electronics from a PV panel onto a thermoelectric. They're looking at the wrong operating point. So you end up losing a load of efficiency, a load of power that you may well have had. And you can kind of see from this graph that without using maximum power point trackers, you waste a lot of energy. So we have a series of different maximum power point trackers for generators at different voltage levels. So here you've got a standard sort of in phase generation 4, I think M250 device, which is really a little bit unreliable at low powers. And again, even as it moves up the power curve, it's still not getting the maximum output power from the TEG. But our converters applied to the same device, you're starting at much lower and you're capturing a bit more power. This is a little bit more esoteric, and there's a lot more software that goes at the back of the converters that enables us to generate more power than a conventional maximum power point tracker. So going from 9.37 to 12.8 doesn't sound like much, but when you deploy it over a much larger scale, that increase is worth having. And again, where we found our expertise were useful is in understanding how devices work and how much power they can generate from a fixed power source. A lot of researchers were fixing a hot side temperature, not caring so much how much power they were putting in, whereas in every practical system, power is limited. Power is limited in some form. And just sticking it in a tester and expecting to get a fixed temperature didn't actually tell you the whole story about the system you're installing. Various efficiency gains are possible using our converters. You may think they're not significant, but when you scale up to tens of kilowatts, they become absolutely worth having for normal systems. It's a huge number of different converters that we offer, right the way down to small energy harvesters that are up to about 5 volts output. They've got different regulators they output with integrated supercaps, lithium-ion batteries, USB chargers, and more standard industrial-focused power converters. And that takes me to the end of my presentation, and thank you all for listening, and I'd be happy to either take questions now, or I've got a booth just pretty much behind you, over to the right. My right, your left, if you've got any questions. Thank you.